All right, welcome to Physics 105. I'm Brother Weber. I'd first like to go over some introductory material. So here's the course description. So Physics 105, it's an introductory algebra-based general physics course. We'll be talking about mechanics, fluids, waves, and sound. Now this is what I expect. You should have an excellent understanding of algebra and trig. And I recommend you take the lab class as well. So here's the requirements. Math 110 with a C- or better. Math 111 and, which you already know by now, you have to pass a comprehensive math exam Wednesday. The test will be given Wednesday or Thursday. And a sample exam is available on Canvas. I already sent this out via email, but I'll go over it again anyway. So you have to take the math exam Wednesday or Thursday on Canvas and take it before midnight Hawaii time. Here's the policies or the rules. No calculator. It's a closed book, closed notes exam. You can't receive help from anybody. The internet, a textbook, anybody. Don't share the questions with anyone. Just basically pretend you're in the testing center. You'll have 2 hours to complete the exam. You'll be monitored by Proctorio. Proctorio is that remote proctoring system. 15 problems. Please check your work. I guarantee you, if you don't check your work, there are a couple of problems you will get wrong. I set it up that way. You have to learn to check your work in physics. All right. Well, I should tell you why I have this math exam. So when I first came here 20 years ago, for the first few years, probably about 40% of the students in physics were getting D's and F's, which is pretty awful. And I realized the reason they were doing so poorly is because they just really didn't understand the math that one needs in order to succeed in physics. So the whole point of this is to motivate you to be prepared mathematically. If you can't do math, you're going to really struggle with physics. All right, what is physics? Physics, it's a fundamental science. It's the foundation for biology, chemistry, biochemistry, astronomy, oceanography, etc. Basically, physics explains how the universe works. Here's a really neat quote from Albert Einstein. The most incomprehensible thing about the universe is that it is comprehensible. And it's the job of the physicist to figure out the laws, basically how the universe works the way it does. Physics is based on experiment. That's incredibly important. If somebody comes up with a beautiful mathematical idea and it doesn't agree with the data, it's trash. Or it needs to be revised, let's be polite. Okay? Here's the attitude of a physicist. We are trying to prove ourselves wrong as quickly as possible because only in that way can we find progress. So I know many of you have served missions, and think back to your missionary days. When you were explaining the law of tithing to people, what did you say? I mean, hopefully you said, how do you gain a testimony of the law of tithing? Well, by doing it. And so that's doing an experiment. So it's the same thing here. Why do we study physics? Well, I think you know that progress in physics has led to many technological breakthroughs in medicine, in electronics, all sorts of things. Computers, NMR, CTs, mobile phones, the whole bit. Basically, you have to understand the basic science in order to make discoveries, in order to know how to apply the science. Law schools love physics graduates. Business schools love physics graduates. Of course, some of you are pre-med students, and you have to have at least a year of physics for most medical schools. Here's something interesting. Some of you may be thinking of going into education. So 20 years ago, we moved from Illinois. We lived in a just average suburb of Chicago, middle class. And the teachers in our high school district went on strike right before the school year was to begin in 1998. And so in the United States we have something called the Freedom of Information Act. So they published all the teacher salaries in the local newspaper. And we were surprised to find out that my daughter's physics teacher, he had 20 years of experience, master's degree. He was earning more than $100,000 a year. This is 1998. So physics teachers in high schools are very much in demand. If you teach at the right school, you can make a lot of money. All right. Physics is required for lots of majors. Let's be honest, that's why most of you are here, correct? And that's because you're going to use this stuff in your classes and in your careers. So I'm going to show you a section of email I received from a former student. This is Sonny Martin. He's now an emergency room doctor in Massachusetts. Let's just read the first paragraph. Aloha, Dr. Weber. It's Sonny from your BYUH physics classes. So I am about halfway through my first year of medical school, and I have been thinking about your classes a lot. Don't ever let pre-med kids trick themselves into thinking that physics isn't important as a doctor. We have recently been studying heart and lung physiology, and the models we use for blood and airflow are exactly the same as the models used for electric circuits. So that's important. I mean, in Physics 106, we're going to learn how to analyze electric circuits. So you might think, I'm not going to do this. I'm not going to be an electrical engineer. Why do I need to learn this stuff? Well, the point is you're learning it because the same models, like he said, that we use in Physics 105 and 106, you're going to apply to the body if you're going to be a doctor or something. So just keep that in the back of your mind. You might not think you're going to use some of this stuff now, but you may be surprised. You may use it later on. So what can I say? Keep the faith, right? Okay, what are you going to learn in Physics 105? You'll learn concepts. You'll learn physics concepts. So you'll learn concepts from the textbook and class. I call this class. And you're going to learn problem-solving skills from the textbook, from the class, and from doing your problem sets. I already sent out the syllabus. I'm not going to talk about that much. I just want to talk about a few things. I expect you to read the syllabus carefully. So let me just talk about a few things. So in class, again I'm calling this class, I'll give short lectures, and then I'll often pause and I'll put a multiple choice question on the screen. And the multiple choice question has to do with what we just discussed. So when we get to those multiple choice questions, I want you to pause the video, read the question, and answer it. The whole point of this is to see if you understood what we just discussed. And also another point is for you to start thinking like a physicist. Now when you restart the video, you're going to see the answer. Please don't cheat. Please don't just go to the answer, because that doesn't do you any good. You need to start thinking about physics. You need to start thinking like a physicist. So actually stop the video, answer the question, and then move on. You're going to be submitting all of your problem sets on Canvas. And so that means you have to make scans. So there's a nice app called Adobe Scan. You might want to use that. If you have another way to do it, fine. But sometimes people take photographs and they're really poor quality, so it's hard to read anything. Okay, every exam is going to be comprehensive. So for example, exam 1 is going to be, let's just say, chapters 1 through 4. Exam 2 is going to be chapters 1 through 8. Exam 3 is going to be chapters 1 through 12. So you have to just keep reviewing. And the reason I do that is because by the time you get to the final, you'll be set, hopefully. We do have a web page on Canvas, obviously, because we're going to submit our homework on Canvas. On that web page, on that site on Canvas, I have all the PowerPoint slides. I'll have these videos. After you submit the problem sets, I'll have the solutions. I have old exams with solutions that I want you to study before you take your exams. I have handouts, all sorts of good things. Study groups. I strongly suggest you work in groups. You'll just learn a lot from each other, and you'll use your time, hopefully, well. So form some study groups. But here's something you have to be careful of. It's fine to work in groups, but do not submit identical problem set solutions, because then you get a 0. All right, that's all I really want to say about the syllabus. Let's see. I should warn, okay, let me talk about the textbook. The textbook is really wonderful. The author of the textbook, Randy Knight, he's an expert in physics education research. Believe it or not, you can get a PhD nowadays in physics education research. Those people study, well, they basically study how people learn physics, what's effective, what's not effective. So he's an expert in the field, and he wrote the book based on his knowledge of physics education research. So it's a good book. Here's a couple of things I really like about it. So he has these stop to think questions. So let's say you read a couple of pages of the physics book, and you know, by the way, reading a physics book is sort of like reading Isaiah. You can't just read super fast. You have to read it slowly and think about it, maybe reread it. All right, so let's say you've read a couple of pages, then you come to the stop to think question. You should always answer these questions. These questions are designed to see if you've understood what you've just read. If you can't answer this question correctly, that means you haven't understood what you've just read. So you need to go back and read it, or think about it, or watch a video, or do something. He also has these notes, which are usually useful. You should read them. He has lots of examples. When you read these examples, I would recommend you do them, don't just read them, take a piece of paper and a pencil and actually go through it. Because, you know, there might be some things that you don't realize, you don't know, and you're only going to find out if you go through them with a piece of paper and a pencil. He has these little notes, kind of really important things that you want to read. And then problem-solving strategies. He has these really neat problem-solving strategies, which if you follow, you'll be able to solve the problems easily, rather than just being haphazard about it. All right, here's a warning. So this is a Physics 105 student. Physics 105, we're going to go really quickly. This is a first half of a 1 year or 2 semester course, 105, 106. It's just like every other algebra-based physics course in the nation. I mean, it's not anything unique, but it's fast. In the calculus-based series, we take 3 semesters to do this material. We're only taking 2. So it's going to be fast. And especially in the spring, it's going to be even faster. So what that means is don't get behind. Don't fall behind. Because if you do, it's going to be very, very difficult to catch up. And physics is not one of these fields where you can cram the day before the exam. Another thing I wanted to point out, physics is about understanding. It's not about memorizing. So yeah, you know, you have last year's exams you can review, but if you think you're going to learn anything by memorizing them, you're wrong. Because you'll get different questions worded differently, and they're going to test your understanding, not your memorizing. Some people have had success referring to Khan Academy or the Chegg tutoring. And so, you know, just if you're having trouble, you know, look outside the box, okay? All right, we have a tutor, a student tutor, Lityan. He's a very nice guy, and he's highly intelligent, and he understands physics really, really well. So we have tutoring hours, Tuesday, Wednesday, Thursday, 6 to 10 p.m., and he's going to use Microsoft Teams. If you've never heard of that, don't feel bad. He's going to send out a document that will explain how to use it. But basically, you know, it's kind of like Zoom or something. You know, you can have face-to-face or you can have groups, whatever you want. But please use Lityan. I mean, he's a great resource. And he needs to make money. And so the only way he's going to make money is if people call him and talk to him. So please use him. All right, so here's your assignment. Log on to the class website on Canvas and just explore so you know what's available. Take the Physics 105 math exam Wednesday or Thursday. please do well. You should really read the textbook's preface to the student, and then I hope you're reading chapter 1. All right, so let's get on with it. Let's go to chapter 1. So chapter 1 is about representing motion. So very few equations. We just want to represent motion. So these are the objectives. We want to understand and use the basic ideas of the particle model. We'll analyze the motion of an object by using motion diagrams. We'll describe motion in terms of position, displacement, and velocity. You already know some of that. And we'll gain experience with displacement as a vector and velocity vectors, and we'll learn how to add vectors. All right, the first thing, the particle model. Okay, so let's say we wanted to discuss the motion of a baseball. You know, that's incredibly complicated because you have to worry about air pressure, you have to worry about the ball spinning, you have to worry about the fact that the ball is not a uniform sphere. You know, there's little fibers sticking out. You have these threads. The ball is not uniform. It's made out of different types of material. It's incredibly complicated. And for our introductory physics course, there's no way you can account for all of those details. So what we do is we make a model. So for example, we say, here, there's the baseball. It's a uniform sphere, period. There's no air. Forget about air. And you know, this captures like 95% of what we need to worry about. So it's good enough. And in fact, this is even too complicated. We're not going to look at the baseball as a sphere. We're going to say it's a point. All right? So that's the particle model. When we talk about cars, we're not going to draw a car. We're going to draw the car as a point. So for quite a while, we're just going to assume everything is a point. And we'll get 99 or 95% of the physics, and it's good enough. All right, let's talk about motion diagrams. So motion diagram is just a tool to help us understand motion. So here it is. A motion diagram is a picture of an object's position at equally spaced time intervals. So here, it just shows you that, you know, the particle's there, particle's there, particle's there, particle's there, you know. That's all. And these numbers are just labels. But the important thing is, so this time is the same as this time, same as this time, same as that time, same as that time, same as that time. Right? That's the important thing. Equally. So it's kind of like this. Let's say this room was dark, and we had somebody in the back with a flash. And the flash went off every 1/10 of a second. So if I moved across the room, you would see me every 1/10 of a second. So that's basically what it is. The position at equally spaced time intervals. Okay, so I'm going to walk across the room now, and I want you to, as soon as I'm done walking, pause the video, and I want you to draw a motion diagram. Okay, so, and I only want you to draw the motion diagram from like here to here. Okay, so basically you don't see the start, you don't see the stop. Okay, so pause the video and draw the motion diagram. All right, this is what you should have, something like this. I don't care about the number of dots. I don't care if you label it 1, 2, 3, 4, or A, B, C, D, doesn't matter. But the important thing is, I was walking at constant speed, right? Constant speed. And so if this time is the same as that time, which is the same as that time, and if it's constant speed, that means that this distance has to be the same as that distance, which has to be the same as that distance. All right? Okay, now what I'm going to do, well, okay, now I'm going to do something else. So watch what I do, then pause the video, and then draw the motion diagram. Okay, and again, so just, you should start from like somewhere around here and stop somewhere around here. Okay, so draw the motion diagram. All right, so hopefully you have something like that. And so why? Well, because I went faster and faster, right? So again, that time is the same as that time, the same as that time. But I was running faster here than I was here, so I was covering more distance. Okay? So what would it look like if I was running really fast and then I slowed down? So that would look like that, right? Agree? Okay, so here's a question. So again, what I want you to do is read this, think about it, come up with the answer. And once you have an answer, then look at the answer. Okay, so in other words, come up with an answer, pause your video, and then once you have your answer, then continue with the video. And by the way, there are 3 correct answers for this one. Yeah, there may be more than one correct answer for some of these questions. All right, so I'm assuming that you thought about it and you chose answers. So here you go. All right, so you can see the black one, the distance is the same between each number, between each location. So that means constant speed. Same thing is true for the blue ball, right? Same distance, same time. That's constant speed. And the black ball moves slower because the black ball is only getting a small distance for the same amount of time. The blue one is getting a larger distance, so the blue one's going faster. All right, here's another one. So think about it, choose your answers, plural, and pause the video. All right, so here's the answers. Okay, you can see that the black ball increasing speed because the distance between the numbered locations is increasing. So the number 1 is going faster. The blue ball, same speed, and that's it. All right, here's another one. So come up with an answer and pause. All right, so we start at A. We start up here, we go down here. You can see that the distance is increasing. So once again, the ball has an increasing speed. All right, pretend I have a board. So here's the countertop. Here's a board. Here's a board. So I'm going to just roll a ball down the board. So please draw the motion diagram for that. And once you're done, so pause the video, draw the motion diagram, and then look at the answer. So hopefully you drew something like that, whatever, other way, right? Because it's going faster and faster and faster. Okay, now the next one, pretend you're throwing a ball straight up. And I only want you to consider the motion right after it leaves your hand and then right before it stops. So draw the motion diagram for that. So pause your video. All right, hopefully you have something like this, right? Because it gets slower and slower and slower and slower. Okay, so all we've been talking about so far are concepts. Now we want to put some numbers. We want to use numbers to represent motion. Well, if we want numbers, we need we have to make measurements. In order to make measurements, you need a coordinate system. You've all seen this before, right? The Cartesian coordinate system. Usually we put plus, plus, minus, minus, but we don't have to. In fact, later on we're going to have some examples where we're going to make that minus. So if we go up, we're going to call that negative direction. When we go down, we'll call it positive direction. It doesn't matter as long as we're consistent. But generally speaking, we'll call going that way positive direction, that way negative direction. That way positive, that way negative. But again, we don't have to. We can do whatever we want to do. I mean, the universe doesn't depend on how we decide to call things positive and negative, Okay, here's a question for you. So answer it. So get ready to pause and so forth. All right, so let's see. Hopefully you all agree. You can't decide because we don't have any labels, so we don't know where it starts, right? We don't know if this is the beginning point or the ending point. We don't know. So we have to have something to introduce or to indicate direction, right? Direction. And we do that with vectors. Okay, so I don't want to do this now, but you should do this at home. So click on this link and you'll see just like, I don't know, 3-minute video clip from that movie, Despicable Me, where the guy talks about vectors. Remember that? Talks about vectors having magnitude and direction. So you should watch that. It's kind of funny. Okay, so a vector is something that has magnitude, magnitude, which is like size, and direction. So what's an example of that? Like force. So if I do that, you know, I hit it hard, so that's the magnitude, and my direction was down. There's also something called a scalar, which is just magnitude. So it doesn't have any direction. So like temperature, right? Temperature doesn't have the direction, so temperature is a scalar quantity. Okay, we have to learn how to add and subtract vectors. In this chapter, all we'll be doing is adding. But don't worry, you'll subtract later on. All right, so here's a vector. So this represents the size or the magnitude. In order to indicate it's a vector, we put a little arrow on top. But usually we're too lazy to do that, so we just do something like that. Just put a line on top. So a vector has a head, that's where we put the arrow, and a tail. Okay, so again, the size is the magnitude, and the direction is given by the direction, you know. Okay, so we have to learn how to add. So let's do that. Actually, let's quit. So that's enough for this video. We'll start up again in a few minutes, or whatever.